Okay, I'm back. Yeah, I don't know if I'll glue the video or I'll upload it as a separate upload, but anyway. So now we're talking about trivial and non-trivial. So this maps all elements of C3 to the all elements of C3 to the identity. Aha. Aha, aha, okay. Really? Okay. That's why they call it trivial. So the name trivial, so the name trivial morphism is related to the mapping being like all to one element of the target group. Yes, exactly. No, yeah, okay, of course, because you can always map everything to the identity, and then that sort of works, right? Understand the groups, definition of define possible images. So I mean, these must be, since C3 is generated by B more by where maps and masters are relations of C3, so B3 equals C. So essentially, these must be true. The order of these must divide by the order of these must divide by the order of B, which is 3. Why is the order of B3? Property of Lagrange's theorem for homomorphisms. The order of elements in... What is the order of an element? Why is this order 2? So what is the... It's the smallest positive integer n such that... Okay. Is how much it takes to get to the identity, basically. So... Okay, so that's why it's saying that it must be the same thing. So... Because essentially the order of B is the order of B, yeah, which is 3. I'm not so sure I understand that part, but yeah, okay, like which works. The non-trivial, so since the order of any element is 1 or 2 and B has order 3, no non-trivial exists. The order condition. Interesting, right? So this is telling me there's no non-trivial homomorphism. So I'm doing something wrong, because this is where I get a contradiction now. So but it's basically saying it's induced by the only possible non-trivial action of C3 on C2 squared. Unless for some reason I really would need to look at these, not at C3. But if it's isomorphic, then it seems like I should be able to take a look at these. But now, that actually... Why only the term? Okay. Ew. Okay, so I might be doing something. I must be doing then something wrong. So essentially, you're telling... So Grok's telling me there's no non-trivial homomorphism between C3 and C2 squared. Because preserves the group operation, right? So essentially, the group operation is just, you know, it basically says, so it's basically telling me that where is Grok? Where's the reasoning going bad? So either this reasoning here is somewhere is bad, or I'm just basically looking at it from the wrong perspective. So we kind of have to define the these of E. We have to define these of B, right? Those are the generators, right? So we need to map, we need to see where these elements map, don't we? That's the point, right? So we're mapping E and we're mapping B, right? So we're mapping, so we need to map, it's a function xy such that phi x times phi y is the same as the phi of x and y. Now C3, okay, no, but C3 has 3 elements, E, B, and B squared. So actually we need to define also, so this is, but I use this at the generator level, or the order 3 is E, B, and B squared, where B3 equals E. It's isomorphic and B has order 3. I guess we need to preserve that, right? So we need to make sure that this preserves the group operation. By where B maps and so we only need to map B. That's where I think. Don't we need to map the? Don't we need to map the 3 elements, not just the generator? So phi E to me is clear that it's phi EE, and then essentially phi B needs to be one of these 3 for this to be the non-trivial. So let's just do one by one. So let's assume it's EA. Let's assume the B maps to, like, B maps to EA. Oh, I think I need to, I can't do it like this. I need to find out, because I don't have a mouse. So essentially, I'm just gonna call it F instead of phi. So I think if these maps to like EA, then this means that B squared equals to EA times EA, which by definition, this is how we defined C3 is EAAE, right? So AA. So this is, no. So that is, EE b squared. There's something that I'm missing here. So if I map B, and I'm saying b squared is just b squared, right? So, but I can also just say b squared is something else, right? There's nothing in here, like in C3. In C3, the way that is defined in group theory, is it correct to say that B equals B squared, or is B squared treated as an independent element? Yeah. So in group theory, C3 is a cyclic group of 3, which can be defined as C3 is E, B, and B squared, where E is the identity element, B is a generator with B3 equals E. The group operation is written multiplicatively, though it could be additive. The elements satisfy BB equals B squared times B equals B3 equals E. Okay, so yeah, that actually powers of B. Yes, that's correct to say that BB equals B squared. Okay, so that is actually correct. So that's something that you have to assume that is correct. But then this means that if B is so if B is EA, then FBB is EA times EA, which in this case is EA squared, right? But the EA squared is not really defined in that's wrong, right? Can you, so okay, wait a second, let's go back to the definition. So the operation is component wise, so is G1 is, okay, it says is GG and HH. Okay, so you don't but if so, EA squared, okay, so the 2, so EA squared is, why is EA squared the same as AE squared? That makes no sense at all. Oh, because that is like these. Okay, so that rule is maintained in here, where C, okay, so that still is maintained. So A squared is E. Okay, so this means this is these, which in this case would mean that makes no sense at all, because this can be F of E, right? So let's say so FB equals AE is going to be the same, but what about if we do AA? Then it means, yeah, that's also the same. You just can't do these. There's no way to map these. There's just no way to map these, because there's just no way to map these. There's no way to map these. There's no way to map these because what we need to make sure is because anything else is going to just cycle too fast, because AA, so if we map B to AA, then FBB would be basically A times AA, which is basically EE, which is basically FE. So essentially we're just like, well, unless we're saying FB is mapping to EE, we're saying FE is mapping to EE, but now FB cube should map to something else, but it cannot be EE. Well, it is, right? Because we just define B like these. So it seems we can find a non-trivial mapping from C3 to C2 squared if we start off by mapping the two, by mapping E with EE. Can we map E to something else? So even starting with EE, we cannot find a non-trivial homomorphism because the order of B3 cannot map to any non-identity element C2, C2. Can we map E to something else? No, we cannot map. How then? But then how is that possible? So define D times S with the action of S on D is induced by the only possible non-trivial action of C3 on D. So the only thing that I can come up with is that we just ignore these and we focus on these, right? But that's the whole point, is that we're doing, like when you're doing this quotient, that actually becomes like isomorphic. So I mean, there must be some, to me this seems obvious that it's impossible, but then like the question wouldn't make sense. So my follow-up question would be, if say group A and B are isomorphic, is it equivalent to find a non-trivial action from A on a third group B? If say group A and B are isomorphic, is it equivalent to find a non-trivial action from A on a third group C and a non-trivial action from B to that same C, because then why do you even give this information on purpose? Maybe to trick the AI, right? It's great. So my question is, if we have two isomorphic groups, is it equivalent to find isomorphism, to find a mapping, to find an action, right? The existence of a non-trivial action from A on group C is equivalent to the existence of non-trivial action. Here's why isomorphism preserves structure. Yeah, I know. That is the point. That is what bothers me. Preserves structure, right? This means A and B have identical properties, order, subgroups, so the capabilities to act on other group C. I'm very stuck. This seems to be impossible. The action of S on D, and S is these. But now we're looking at an action that is induced by the only non-possible, like this assumes that there's one non-trivial action of C3 on D, and D is defined as C2 squared. Now the question is, maybe that is not C2 times C2. You know? So in group theory, that's maybe what I'm getting it wrong, and where well, I mean, Grok's not getting it wrong, but like it just doesn't make sense. So in group theory, is the following the same as the direct product of C2 with itself, or is it the element-wise square of C? That would be another interpretation, right? So is ambiguous, so let's carefully address the question whether it refers to the direct product or the element-wise square of group C. Since your first question, direct product, interpreting D equals C squared. So this group theory typically has one of two meanings, depending on the context: direct product or cyclic group of order 2 to the 4. Okay, so in some contexts, Cn2 denotes the cyclic group of order n squared. So C22 could mean C22, C4, the cyclic group of order 4. However, this is less common when referring to groups like C2. Given your earlier question about the concept of C3D, the most is a direct product again, but it's not. Like, ignore my previous question. Let's try again. It must be something different. No, just like, can we just ignore this new question? So in group theory notation, how is these to be interpreted? Like, I just can't, like, it's a direct product. Really? Really? The thing is considering all this in here. So what if I try just perplexity? I'm just gonna ask perplexity the same question, because I'm like, I think that could be the problem, right? It's telling me the same. Okay, but then I'm stuck officially because I can't find a non-trivial. I can't find a non-trivial But the only possible non-trivial action, I can't find a non-trivial action from c3 to c2 squared. Great. We're gonna continue next time, I guess.